Okay, well, good morning. I'll start with my usual summary, but if there's any questions from the classroom or anyone online, you can put yours in the chat. Hang it in there. Ready to start project 2? We posted it this week. Cool. Okay, so we've been working on the, you could think about it as properties of matrices or properties of sets of vectors in Rn to bring linear combinations and linear independence all together in kind of a unified framework. So for us, Rn and column vectors are the same thing. So if we have a matrix, it's just a way of stacking up vectors in Rn in a uniform way. So we take a matrix that's n by m. We define its range space to be the set of all points in Rn that look like A times x, where x is in Rm, and we prove that that's equal to the span of the columns of A, and that's called the column span. So you'll see different books talk about the range, and different books talk about the column span, but they're exactly the same thing. The span just takes a set of vectors and generates all possible linear combinations. So it's just a compact notation to say, given these vectors, generate a subspace that contains the vectors. And you do that by closing the set under linear combinations. And since the columns have n components, they are vectors in Rn. And so this gives us a subspace in Rn. The null space of A is the set of all x in Rm such that Ax equals 0. So because A is n by m, it is multiplied by a vector that is m by 1, then we get an n by 1 vector. So it's a set of all things that get mapped into 0. And then instead of writing it in terms of x1 to xn, I just wrote that in terms of alpha 1 to alpha m, because that's how we like to think of a solution sometimes, is just a set of numbers. But also when we write linear combinations down, we like to put numbers in front. And A times x is just x1 times the first column of A plus x2 times the second column of A, etc. It's a linear combination of the columns of A. So the null space is looking at all the different ways you can add up the columns and get the 0 vector. If the columns of A were linearly independent, then the only way you could get the 0 vector would be with all of the coefficients being 0. Then your null space would be the 0 vector in Rm. So the rank of A is defined to be the dimension of the range of A, and dimension is number of linearly independent vectors in a set. And the nullity is the dimension of the null space of A. So essentially the rank is, yes, the number of linear independent columns in your matrix. The null space is measuring the number of linearly independent solutions you can build that give you the 0 solution. So it's really the number of dependent columns in A. So the way you get a non-trivial vector in the null space is you need to do a linear combination of the columns of A and get the 0 vector in Rn. And if you can do that with some of the coefficients being non-zero, then these vectors are linearly dependent. And so the dimension here is the number of dependent columns you have, or if you're working with originally a set of vectors, you could have just stacked them up as the columns of A, your vectors. And so whether it's columns of a matrix or vectors in Rn, for us, we go back and forth and it's the same thing. So it's kind of cool. Rank measures number of independent columns. Nullity measures the number of dependent columns. Now, there's only so many columns in a matrix, and the sum of those two numbers is the total number of columns in the matrix. That's the rank nullity theorem. So this is very useful to know. And what I'll have you doing in the homework you will start on Thursday of this week is you'll give you several matrices and have you calculate its rank and its nullity. And you will observe that they always add up to the number of columns in the matrix. But if you think about it like this, it's kind of a foregone conclusion that it has to work out that way. So proving this is not exactly easy, but it's a kind of an intuitive concept I think you can grasp. Now this was really our pro tip because we proved A alpha equals 0 if and only if A transpose A alpha equals 0. So the dimension of all the solutions that give you A alpha equals 0 is the same as the dimension of all the solutions that give you A transpose A equals 0. So nullity of A transpose A and the nullity of A are the same. Now, once you know the rank nullity theorem, then once the nullities are equal, the ranks have to be equal because they both add up to M. So there's no, okay, because A transpose A and A have the same number of columns. Now, once you know this, you get this one for free by just replacing A with A transpose. So you would think of this as being some matrix, whoops, go back. You would think of this as being just some matrix M, and then you substitute in M equals A transpose for this result, and then you get this one by just swapping A and A transpose. So that's for free. This one is a little bit more work, but what you end up proving when you look at A times B is that its columns are linear combinations of the columns of A. So I proved that at the end of the chapter now, but I don't think you really need to go through the proof. But what it says when you multiply two matrices, you cannot increase the rank. And it's because A times B, if it's really linear combinations of columns of A, you can't create independent vectors by doing linear combinations. All you can do is create dependent vectors. Like if B is the 0 matrix, whoops, A times B has no independent vectors then. But if vectors are dependent, you can't add them together and make them independent again, okay? So multiplying by matrices, the intuitive thing to take away from here, when you multiply, you cannot increase the rank. So it's upper bounded by the rank of A. The most surprising one on here, and really highly, highly useful, is that the rank of A and A transpose are always the same. Now I have a confession to make. You know, I'm a professor. I teach this stuff all the time. So I've known and used this since I was a student as well, not as a freshman, okay? I didn't learn linear algebra as a freshman. I learned it as like a junior, and then really learned it in graduate school really well. But I had never proved this for myself, okay? So I did the first proof for myself a week ago. So if you have a hard time believing this is true, I get it, but it's something so useful to use. And let me show you one of the consequences you get. So by the rank nullity theorem, the rank of A has to be less than or equal to the number of columns. It can't be more, because the dimension of the nullity is either 0, 1, 2. It's a non-negative integer. The rank is a non-negative integer. So neither of these can exceed M. So the rank of A is upper bounded by the number of its columns. But if the rank of A transpose is equal to the rank of A, well, how many columns does A transpose have? It's the same as the number of rows of A. So the rank of a matrix is upper bounded by the number of rows and the number of columns. And so the thing is, you might have a matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You might ask yourself, how many linearly independent columns can there be there? And there's how many columns did I make? 1, 2, 3, 4, 5. Okay, I was ambitious. 5 columns. Can they all be linearly independent? And the answer is no, because the number of linearly independent columns is less than the minimum of the number of rows, which is 3, and the number of columns, which is 5, so it's less than or equal to 3. So you can find potentially 3 linearly independent columns, but you can't find 4. Okay, so as soon as you have vectors that are in R3, then the most number of linearly independent vectors in that set you can ever find would then be 3, because you just stack those things up in a matrix and you have rank of A equals rank of A transpose. And we know ranks are upper bounded by the number of columns, but the number of columns in A transpose is 3, because here's a column, here's a column, here's a column in A transpose. So this is super, super useful. The other ones are nice to know, that the rank of A and the rank of A times A transpose and the rank of A transpose times A, they're all equal to the rank of A. Okay, so those things are very, very fun to know, but this one is the one that ties it all together. And the reason you should believe it is if you look at how null space is defined, it's building linear combinations that are dependent because they add up to 0. And the dimension of that is the number of dependent columns then, but rank is the number of independent columns. So columns can be grouped into independent and then those that are dependent on the other columns. And that's how you build non-trivial solutions to AX equals 0. Super cool? Almost. Okay, there's a tremendous amount of insight to be had if you dig into that, but it's okay to just take these as a list of facts and use them when you're solving linear algebra problems. And then later on, maybe when you're juniors or something, you might take Math 217, which is the theoretical version of linear algebra with all the proofs, and then you'll be ready to digest why these things are true because you've used them and you felt comfortable with them. Would be a good suggestion. And then this is just recalling that we have this thing called a basis. It's a set of vectors that are not too big, meaning they're linearly independent. So anything dependent, we've removed it. And yet it's big enough, so it's not too small, because when we generate linear combinations from the vectors, we get everything in our subspace. So that's the notion of a basis. Not too big, all the dependent vectors are gone. Not too small, by doing our natural operation, which is linear combinations, we generate everything in the set. So for me, that's how I remember what a basis is. The intuitive concept, not too big, linearly independent, big enough, I can generate everything in V. And then dimension is formally defined as the number of vectors in a basis. And so that gives us notions of rank, nullity, etc. Well, that's a lot of facts about matrices and subspaces. I'm going to give you guys time to just work through that and take it under advisement that you do, even if you're doing really, really well, that you build your cheat sheet, this week's homework assignment. And what we're going to work on now is just some geometry in Rn, and I think you'll find it to be actually quite fun. So we've done the hard work. By you guys fighting through linear combinations, linear independence, bases, span, the rest of this is just using it, and we're going to get some amazing things to come out. Okay, so this is fun geometry in Rn. Our hard work is done. Let's reap our rewards. Yes. Okay. Let's see if I can live up to our my advertising. So let's do this. Let's let U be a vector in Rn. And we'll let V be another vector in Rn. Okay. The dot product of U and V is U with a great big dot in there, V's. So it's not the little dot that we use for A dot B to denote matrix multiplication. And this is by definition equal to the sum I equals 1 to n of ui times vi. So that's the first component of u times the first component of v, plus the second component of u times the second component of v, the last component of u times the last component of v, and you add them all up. I wonder if that looks familiar to us. Okay. Well, so what happens if I do U transpose little dot times V? I transpose U, I make it a row vector. I don't transpose V. And then this multiplies this, and this multiplies this, and this multiplies this, and you just add them all up, right? That's what U transpose times V is equal to. So that's U1, V1, plus U2, V2, plus dot, 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 UN, Vn. So we conclude U dot V is the same thing as U transpose V. Okay, that's fine. That's cool. Now we're going to use it in a very different way, but its calculation is super Super easy. You just take the first vector, you transpose it, and you multiply it times the second vector. Now in Julia, there's a command called dot, and you go dot of u comma v. It does the dot product for you. And if you don't want to use the dot in Julia, then you do u transpose times v, and you've got the dot product. Okay. Now here's the thing, in mathematics, notation is still floating around. It's not 100% fixed yet. So another name for the dot product of two vectors is inner product. Yeah, it's painful to have to remember all these different variants. It is painful. We'll be consistent in Rob 101. But if you go into a physics course and your professor uses inner product, then you'll say, okay, yeah, I've heard of that. Most likely your physics instructor will say dot product, but if you take another math course or engineering course, then we will see inner product showing up. Okay. When do we get a vector when multiplying vectors? So that's a question from the chat. Here, let's notice that U transpose is 1 by n, and this is n by 1, so the product has to be 1 by 1. Get out of there. Okay, so the way we've defined it, there is something called an outer product where you take U times V transpose. And that would be n by 1 times a 1 by n, and then you would get an n by n, but we're not doing that. That's called an outer product. So another notation here is U comma V with brackets, and that's the same thing as the dot product. So we'll stick with dot in Rob 101. It's the first time in my entire career using the dot notation, I'll be honest with you. In most of the control courses and things, we use the word inner product, but each little subgroup of applied mathematics type people have their favorite notation and their favorite vocabulary. It's sort of like tribes, okay? We've got the control tribe, we've got the communications tribe, we've got the physics tribe, we've got, okay, and we all use slightly different language, which is unfortunate, very unfortunate, okay? But at least we're not treating complex numbers as something that is totally crazy and believing that they're only imaginary, et cetera. So we have evolved past that, okay? So that's a good thing. Okay, so the dot product is really U transpose times V, and it's a 1 by n times an n by 1, we get a 1 by 1. There is something called an outer product, but I will not write it down because I don't want to confuse you with that. Okay. Let's just compute a few of these and just realize. So compute, that is no big deal. Let's say U equals 1, 0, 3. And V equals 2, doesn't matter what I put there, 4, 1. So you guys can probably compute it faster than I can write it down. U dot V, first components multiplied second components multiplied, third components multiplied, and you add them all up. And that's 2 plus 3, and you get 5. Yay. Just to exercise the other vocabulary, compute the inner product of u equals 1, 0, minus 1, 0. And v equals 0, 1, 0, 1. Ooh. Okay, let you catch up, writing that down. And so, let's just do the dot product as u transpose v. 0, minus 1, 0, 0, 1, 0, 1. Okay, so if you forget the dot command in Julia, just go u transpose times v. That you guys know how to do. And so here, first components multiplied, second components multiplied, third components multiplied, fourth components multiplied, and it all adds up to 0. Ooh. Okay, turns out that vectors who have inner products of 0 are like super interesting. Okay, it means they form a right angle. We'll see that, okay? But it means they form a right angle, and it's a way of generalizing the notion of being at right angles to Rn, and that's going to give us a really, really cool result that I will explain in just a few moments. So, definition. Two vectors u and v in Rn are orthogonal if their dot product is equal to 0. Okay, so these vectors we just computed, u and v up above, their dot product was 0. They're actually orthogonal vectors. And there's a cute little notation people use. Notation. One says that u is perpendicular to v. Read as u is perpendicular to v. Or read as u is orthogonal to v. Isn't it wonderful that there's almost 2 pieces of vocabulary for every single term? Okay. Okay, in LaTeX, this is \perp, okay, because it means perpendicular. Okay, so a clean way to write down, you can say u dot v is 0, but people tend to write u perp v. U perp v, meaning u is orthogonal to v. And you can extend that to sets of vectors. Okay, so let's do an example of these things. And we'll do it in R2 so that we can picture clearly what's going on. So here's U, and then this is the V that I chose. Okay, and so this requires, you know, extreme measures when it comes to me doing a graph. Make this 1, this 2, 1, 2, that's a little bit slanted there. Come on, line up. Hey, I did it. 1, 1, and then 2. Oh, those are 3. Gosh, hoser. 1, 2. There, I think the units are the same on each side. It took me so long to do that. I gave you guys a chance to catch up, I guess. So let's plot the two vectors. So U has X component 1 and Y component 2. So here's U. And V has X component minus 2 and Y component 1. And here's V. Well, it should be a straighter line than that, right? Okay. Now, you can check that this is a right angle. Their dot product, let's just do that really quick. Over here on the side, be fine, I guess. U dot V equals 1 times minus 2 plus 2 times 1 equals 0. I believe from my high school geometry, that's a 60-degree angle, and that's like a 30-degree angle or something, okay? So those add up to 90, so what's left over? That is 90 as well. So it's a right angle. So being perpendicular means they form a right angle. So, fact. In R2, U perpendicular to V if and only if U and V form a right angle or, well, if one of these is the 0 vector, guess what? U dot V is 0, okay? Or one of the vectors is the 0, at least one of the vectors is the 0 vector. They could both be. Okay, and then this is used to generalize angles to Rn, but will not do that. You know, we have to make choices, and we're not going to pursue just angles in Rn. It's enough for us to understand right angles. But you can define the angle between two vectors using the dot product. And once you understand how it works in R2, you can take those and use them as the basis for in Rn. So the mental picture I want you to have is that if you have U orthogonal to V, And neither one is the zero vector. So U is non-trivial and V is non-trivial. If they're orthogonal, that's a generalized version of a right angle. That's the picture to have. And it's hold true in Rn. Now, can you picture this in R17? Not very well, okay? So don't worry about picturing it in R3. Some of you are struggling with you can't picture things in R3. And my problem is I'm not very good at that either, but I don't care because nobody can do it in R4, okay? So fine. I'm not so good in R3. Others can do 3D geometry really, really well, and if you can, that's a talent. You should go into mechanical engineering or aerospace engineering for sure, or not, I guess. But anyway, so that's the dot product, U transpose V. Some simple properties that are useful. If I do U plus V dot W, it's just U dot W plus V dot W. Oops. Why? I mean, look, if I do it like this, so that's U transpose plus V transpose W, and you guys know that when you multiply matrices, it adds, okay? So that's U transpose W plus V transpose W, and then that's our definition of U dot W, big dot, plus V big dot W. Okay, so dot products, they just expand them out just like you normally would, numbers and things like that. So the dot product does that. And then if you have, say, alpha in the reals, and you do alpha U dot product V, surprise, that's alpha, and then U times the dot product of V. So you can do linear combinations of vectors and do their dot products, and all of the rules simply follow from you understanding how A plus B multiplies C when A and B and C are matrices, okay? It's just those rules. Hanging in there so far? Question on chat, is the cross product the outer product? No. Man, there's so many products out there, but it's not, okay? The cross product of two vectors gives another vector that's orthogonal to the first two vectors. It's a crazy operation, but they're very useful in electromagnetics and stuff like that. Not gonna help us, and control people don't need it, so I don't think it's important because I'm a control person. Okay, now what I'm really learning in teaching you guys linear algebra is I need to reverse the process that I learned things because I was maybe taught in an old-fashioned way, but also I like formal mathematics, so I like the abstract definition, and then I like to see the example. What I think I'm learning from looking at your answers to problem 1 is you guys want to see the physical thing that motivates the abstract example first. So that's why I'm going to try here and see if this works better than we did when we attacked linear combinations and linear independence. So where we are headed. Okay, and that is orthogonal matrices. So let Q be an n by n matrix. Ooh, we haven't used Q for a matrix ever. We always call them A, B, C. We haven't got that far down the alphabet. We use P for permutation. I guess they don't use O because it looks too much like a zero, okay? It's not the zero matrix. It's going to be Q for orthogonal. Okay. Then Q is orthogonal, or an orthogonal matrix if Q transpose times Q is the n by n identity matrix. Ooh. Now, if I have a matrix and I multiply it by another matrix and I get the identity, what is this matrix? It's the inverse. Yeah, I mean, that seems like way too cool, right? So, yes. This means Q inverse is equal to Q transpose. Okay, whoops, not what I wanted. I wanted you. Come on. Oh well, cut off part of my inverse, you guys will live with it. Now, how hard is it to compute the transpose of a matrix? It's a snap, okay? How hard in general is it to compute an inverse? It's just a royal numerical pain in the neck, okay? Computing inverses. So these matrices are magical. This means you can invert the matrix by simply computing its transpose. So that has to be useful, right? I mean, there's no doubt. That has to be a useful property. Okay, give me QX equals B and I will solve it by X equals Q transpose times B. Done, okay? So that would be amazing, 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 okay? Now, here's a fact, and we will show this, but it's going to take a little while, but not too much time. Fact. Every non-singular, make me write it this way, every non-singular, that means its determinant is not equal to 0, every non-singular matrix A can be factored as A equals Q times R, where Q is, I'll let you catch up. Yeah, and we're going to have this really cool algorithm that just starts out with a matrix whose determinant is non-zero, and just go for it, where Q is orthogonal. And R is upper triangular. Okay, when we get to this, it'll be called a QR factorization of a matrix. Okay, and we'll prove if the determinant of A is not equal to 0, that means, of course, we already know it means its columns are linearly independent, that we can write the matrix as a bunch of orthogonal vectors, etc. So Q being this, but the consequence is, suppose I have, whoops, I can't do it with blocks. I have AX equals B, and I know A looks like this. Well, that means QRX equals B. Then I do what? I multiply by Q transpose on both sides. And the reason is I do that is because this is now the identity. I get Rx equals Q transpose times B, and then I use back substitution, and I'm done. Okay, so if these orthogonal matrices can really be found, life is super sweet, and they are, and computing them and finding them is about the same level of difficulty as LU, but if it's anything else, it's easier than LU. Okay. Does this seem cool? Like, question?
What is a singular matrix? Is it the identity?
Oh, yeah. Non-singular means determinant of A not equal to 0. You can also say invertible. Yeah, I don't think we'd use that vocabulary, non-singular. That's my fault. My bad, my bad, my bad. Okay. So if A has a non-zero determinant, so it's invertible, it can always be factored as an orthogonal matrix times an upper triangular, and that makes solving linear equations trivial, because you multiply both sides by a transpose. How are we doing? We got a few minutes. Okay, so let's just figure out what this Q transpose Q equals identity really mean. Okay. So I'm going to break Q into its columns, and I'm going to do it with a 3 by 3 example. Okay, so I'm just going to take a 3 by 3 example. So then Q transpose, we take columns and we turn them into rows, and we stack them up. So there's the transpose. We can take rows, turn them into columns, or we can take the columns and turn them into rows. It's the same thing. And since I gave it as columns, then these have to be rows. So the VI here are in R3, just to make the computation straightforward. Now, Q transpose times Q then, whoops, this is all of these rows stacked up. And these are the columns. That's an equal sign. And for us, this has to be the 3 by 3 identity matrix. Okay, so if you use what's called the finger following, or finger tracing method, where you take the rows times the column to get the ij entry, this entry is this vector times this vector, so it's a dot product of v1 with itself. This entry is v1 times transpose times v2, so it's the dot product of v1 with v2. It's 0, means those vectors are orthogonal. And this entry is v1 transpose times v3, so it's the dot product of v1 and v3. Okay, so my clock has ticked over. I will pick us up here, and we will write down the consequences of how these vectors and the columns are related to each other, and then we'll find an algorithm that produces that property for us. Okay. We're kind of on easy street for a couple of days, maybe even for the rest of the term, to be honest with you. We've done the hardest part of the job in Rob 101. So thank you.